difference. Yeah. So a reminder, homework 1 is due Friday night. Toward the end of the class today, I'll talk about the last 2 questions specifically, and that has something to do with today's topic. So I want to make sure I do that in the next 30 minutes. I'll pick and highlight some of the points here in the slides. I will not talk about every point, and some of the points are intuitive. So you can read them, read more of textbook to understand the point. The first biggest point here is overfitting, and why is it so important? If you're taking the other course that I'm giving online asynchronous, in that course I also explain overfitting quite extensively, but not as soon as now. That would be toward 1/3 of the course, maybe the 5th week. I'll start talking about overfitting and cross-validation. But through that course, I think you'll have a better, sort of a more enriched understanding and discussion about overfitting. And here I'm trying to highlight the point. Overfitting is a problem because what? What do you think? If you have read the book, you probably have a notion. What's a fundamental reason why overfitting is a problem here? Go ahead. No, this is not competition.
Okay, sorry. I think overfitted models have a tough time generalizing to other data just because it's so hyper-focused on the training set that it basically can't take a brand new set of data and actually work effectively. So it changes the training set.
Good point. Anything to add? Yeah, great. If your goal is to train or to select a predicted model, and it has challenge in getting it right on new cases, such as a doctor after 5 years of training can recognize the underlying disease based on the symptoms. If in trying to diagnose new patients, the doctor is not good at doing that, one of the reasons is perhaps the link between symptoms and the underlying disease, the causal effect is not clear. So I guess the doctor didn't do a good job in studying, and I think that should speak to the same idea here. The link between what is changing at the data level and what is actually driving the change, or what is, what differences in the outcome, which we call target, the differences in the target values that correspond to the changes in the input features, the link between them, if they can be used to predict new cases, they should be generalizable, and they are the patterns. But sometimes you have linkages between the target labels and the input variables that are not useful to predict new cases. That's what we call noise, but this is tricky. How do you know? Let's use the doctor's case. If coughing indicates that there's a common code, when you see a symptom of coughing, you could diagnose that the disease is common cold or bacteria. but it doesn't have to be, right? So in this case, concluding the relationship between the disease and the symptom based on only a few cases, or based on small number of cases, will probably result in overfitting. And here, overfitting is drawing conclusions based on associations that are not generalizable. Hopefully that makes sense. Concluding that the disease is common cold by symptom of coughing is somehow ignoring the other symptoms, and to come to the conclusion that are not generalizable. So overfitting is the root reason for overfitting is because the power of the algorithms. So that's basically that's the driving force. There's always room for overfitting because the model doesn't know good enough. The model is drawing conclusions based on too few examples, like what the doctor is doing. Doctor is not studying very well. It's drawing conclusions based on few knowledge, I guess, and narrow understanding, and the diagnosis is not generalizable. Same thing with computer algorithms, based on too few data and based on the correlations in that few data points that are actually spurious or coincidental in a way. The algorithm is not able to predict to make generalizable predictions. And so there's a tension here. When you have a powerful computer and few data sets, the computer will overgeneralize the correlations here in a way that the computer memorizes all the cases and try to force fit the conclusion, right? Does that make sense? So let's say, what if you have a big enough data set that reduces the likelihood of overfitting? But in these days, it's hardly likely the case. It's almost always the other way around. You have a powerful computer. Any computer that you pick up in the store is powerful enough for any of the data set of most of the businesses have in their control. A i3 CPU is powerful enough to crunch data sets with 1 million or more rows. So that's not a lot. That's not a lot, but the CPU is so powerful right now. So that makes it the main reason of overfitting. In thinking about the tendency for a model to be overfitted, I talked about the power of computer. And when you can translate that understanding into the specific context of the models. We have models that are more complex and models that are less complex. We can actually sometimes limit the power of computer by using different levels of models. When we use simpler models, the power of computer is confined so that it will not try to get more complex because the model itself is setting up a boundary there. So we probably have a little thoughts here and discussion is in several modeling frameworks. Let's say one is regression, where a regression model is a multiple regression, or it involves multiple factors, and these factors will linearly decide your decide the formula or decide the algorithm. The outcome is a linear combination of these factors by using their associated coefficients, right? So it's a linear model still in a multidimensional space. It's a line, basically. It's a line trying to predict the boundary, or the line trying to predict the number. So that makes the model, that at least put the upper boundary of complexity to the model. The model cannot be more complex than the straight line. But neural network is a very complex nonlinear model. It involves very complex curves and boundaries to specify how to predict the cases. So that's the two different levels. But under each of the modeling framework, you can still have different levels of complexity. Let's say, let me ask you a question. Just think about it. In a linear regression model, how do you increase the complexity of the model? By not changing the model framework, let's say it's still a linear regression, but how do you moderate the complexity of the model? By adding more variables, exactly. Or by adding complexity of variables in terms of square terms. That will introduce a little bit curve to the model, although the framework is still linear. So that's how you increase the complexity. If you say, by taking the square of a variable and include that square term besides the original variable itself.
So that's the original variable and then the square term,
yes.
That's not collinear?
That's curvy, but the modeling framework is still linear. It's a little, yeah. I know what you're thinking. It makes the model slightly nonlinear, yes, but it's still not as complex as the real nonlinear models, right? Because of the structure. The structure puts constraint on it. But anyway, you get the idea. To limit the complexity of the model, you can limit the number of variables you include. So only include two variables. You have to select the best two variables to include. That is one effective way to control overfitting. But there are good ways to do that. That's one way. What about neural networks? Probably haven't read about it yet, but you may have a notion of what neural network look like. They have different layers. They have different layers. It's like the neural reflection path, right? If it's the longer the path is, the more complex the model is. So by adding more layers, the model becomes more complex. It allows more room for overfitting, that's for sure.
You mean like more seeds to start with?
More, what do you mean by seeds?
Don't you do neural networks by dropping like a certain number of seeds and then seeing?
Nodes, if that's nodes, yeah. In computational models, the way neural networks, or the way conventional neural networks work, is you have different layers, and then under each layer you can have different number of nodes, or neurons they call. So that's neurons. The more the number, the more complex the model is, because it has more coefficients. Has more coefficients. So you can moderate the level of complexity. And that is a good way to think about, I guess, the tendency for the model to be overfitted to the data. The more complex it is, the more tendency it will do that. But how do you think about that question? In order to get better in predicting the other sample outcome, which is, data point, the test data outcome, outer sample means those data points that are not used in the training process. That's outer sample. We call outer sample, we call test data, we call unseen data, which is data not being used in training. Isn't it the purpose of your training to have a better model to be able to predict out of sample outcomes? By having a more powerful model, you have more potential to land on a model specification that is better able to predict the out of sample, assuming the problem is not too easy. But the problem is complex. Don't you favor a more complex model to start with? More complex models have more ability to detect patterns, at least. Some patterns are not easy to detect, especially for, let's say, the visual cues, visual features of different objects, humans, animals. It does require a complex model. That's why computer vision hasn't been very successful. I mean, in terms of coming close to human performance level, computer vision models hasn't been good enough until deep learning come along. And deep learning models is much more complex than earlier generations of neural networks. So in a way, you need more complex models to have better outcome. But more complex models tend to be overfitting more likely. How do you solve that tension? So that's a challenge. You will become better in dealing with this, I guess, a dilemma. You'll be better at dealing with this dilemma in the actual practice of training machine learning models to understand what's going on in the back and to follow a procedure to do that. So that's how you'll do. This example illustrates, I probably don't have time to go through that, but it's easy to get it. It's intuitive. Let's say we have a simple problem, right? Is to predict the color of the point. And these are the data we have. We have two variables of x and y. And this problem is simple because you only need two variables. You basically only need two variables to be able to differentiate the colors of the points at a reasonable accuracy, because they are pretty much separated. Although there's a blurry line in the middle, it's pretty much separated. So this problem is easy. So you cannot use very complex models. Otherwise, you guarantee that the model will overfit. As the simplest model would be to draw a straight line, which is vertical or horizontal. That's the simplest model, because by drawing a horizontal line, you're only using one variable. You're not using the other variable. The other variable doesn't matter, right? Because it's a straight line. Or if it's a horizontal line, you're using the other variable, not this variable. So that's the simplest model. Here, do you imagine a simplest model? I would say x is better than y for sure by looking at these data, because they are kind of left and right separated. Do you think you can be satisfied with any model by picking an x and draw a vertical line so that you say this model pretty much separates the two colors at the point? Would you say that? If I draw the line here, it will miss these points and mistake them to be gray, and it will miss several of these points and mistake them as dark. No matter how you shift the line, it's always going to make some mistakes. But considering that all of these other points are pretty much correct, accuracy might be close to 90%, right? It's a good model to start with, but maybe there's room to improve. You can slightly increase the complexity now by considering both variables. When you consider both variables, you can draw a line that's tilted. That's when you utilize both variables, right? If you can draw a tilted line somewhere here, this line makes two or three mistakes about the dark points and 3 or 4 mistakes on light points. That's better than a vertical line, for sure. And that's pretty clear because the model is more complex and more powerful. But if you keep increasing the power of that model, you start going to a curvy line where it makes no mistake. That's great for the training set. But can you reasonably trust this model and throw in other points that you don't know the actual label, and hopefully this line will get all the rights in these region, all the points in these region correctly? I wouldn't trust that much because this line is, as of currently, it's exactly overfitted. It makes a curve just to get these points right, right? It makes this curve just to get these points right. And just to be able to make no mistakes about these 2 points, where in fact these 2 points are so close to each other, it's not reasonable to expect any model would be able to differentiate them. And in fact, this point may even be erroneous. The data may have some problem. If you build a model to try to predict data that probably has some problem, your model for sure will be overfitting. Does that make sense? If the patient misreport the symptom, you'll for sure misdiagnose. But is it a good practice to base the model on potentially erroneous data point? That's not, right? You have to catch the big pattern. The big pattern is the fundamental information here. So that's the point. This is what we call a fitting line or overfitting line. And the way to look at it is, if we train a bunch of models, going from simplest to more complex, you can imagine these number may refer to number of parameters of a neural network. If it goes from very small to very large, the model is becoming more complex, right? And assume each of these models are fully trained by using the same data set, same training set, and to the extent that the model achieves its convergence, let's say, the model converges and finishes training, and then you calculate the performance level by using this. In this example, is the error rate. It's time. The error rate is the number of mistakes that the model makes. So the higher, the worse, right? So this is, let's say, misclassification rate. Let's say, right, out of 100 cases, how many mistakes is the model committing? And the 2 lines refer to the training set as well as the validation. Training set is the set of the data set that the model is trained, where validation set is not exposed to the model at all. So when you have train a model to its best state possible, and try to maximize the try to minimize the error rate on that training set, it achieves this level of performance. And when you test that model on the validation set, it achieves some other performance level. Most likely, the validation set performance level should be worse, most likely, but not always. In this case, it's better, right? Because it's lower. Lower is better here, but that's more like unique cases. And as you increase the complexity of the model, you have a line typically look like that. And the thing to recognize here is that if you keep increasing the complexity of the model, you will see that the two lines will move in the same direction at first, and they will diverge and move in different directions eventually. That's almost guaranteed in all the cases if you generate the graph by following that procedure. And the key to understand here is that the line that keeps moving in one direction is the training set. Why? If you keep increasing the complexity of the model will eventually get very good in predicting the training set to the point that it makes no mistakes. So the line will keep going and going and going. But the line for validation set, at some point, it's going to reverse. Why? Because the model is starting to overfit to the training set to compromise its ability to generalize the pattern to a new data set. So always remember that the line that goes back is the test set or validation set. And if we have the y as the error rate, which is badness of performance, is worst performance, the line will look like that. If we have the y showing the accuracy of the model, the line will be concave. If it's error, the line will be convex. You know, it's like there's a dip. If the line is showing performance, there's a peak. So, you know, you want to make sure you're reading the line correctly by paying attention to the criteria here. But in either case, the line that keeps going in one direction is the training set. The line that reverses is a validation set. What's the difference between these, the different points on the X line? Is the complexity of the model. The more complex model always are to the right, right? It starts from a very simple model. Also, you want to make sure that you're comparing apples with apples. You're comparing neural networks with different levels of complexity. You're comparing regression models with different level of complexity. You don't compare regression models with neural networks on the same graph. You don't do that. Although you can have different lines to indicate different models. But when you compare training and validation set, trying to find the best model, you should compare apples with apples, right? And how to spot the best model is to choose the right level of complexity of the model so that it achieves the best performance on validation set. That makes sense? That's when the level of complexity of the model helps achieve the highest accuracy on new data set, basically. That's a validation set. So only pay attention to the validation set line and try to find the point that optimizes the performance over there. So here, if the criteria is errors, you want the least error. So you want to find the dip in validation set line, which minimizes the error rate. And one common mistake here is one will find the cross point of the two lines. That's never relevant. The cross point, there may not be any cross line. In some cases, the cross line is irrelevant. What you want to find is the optimal point in the validation set line. In the case of performance, you want to find the peak of the validation set. In this case, there's no crossing, right? So don't be confused. The crossing is not relevant. Questions? So try to read more. The book use examples to illustrate the point, but the graph will look very same. Even if the graph don't look the same, try to find the same features. There's always going to be two lines. This is based on train test split set, and one line always go in one direction, the other line will reverse. So those are the common features of the different ways you draw the fitting line. That's the optimal model point. More videos on YouTube to try to improve your understanding of overfitting, and then train test split. So let me talk about the homework when I talk about these, when I have limited time here. The last two questions of homework 1 ask you to, maybe the third to the last question, I don't recall specifically. One of the questions toward the end asks you to conduct a train test split, right? So follow the tutorial or follow the demonstration videos. It shows you how to do a competent split. Question 12 asks you to perform a train test split. So follow this procedure, it should be all right. After you have the split, now you have two sets. You have the train and test set. Is it called test set? Yeah. Now the task is to conduct hypothesis testing. So the concept of train test split is to preserve a portion of the original data set to imitate out of sample data so that you can faithfully test your model. That makes sense? Because in the machine learning environment, if you use all the data to train, you lose opportunity to really test the model until you implement the model in your business, and somehow you find the model has overfitted, and that's too late. It's already making mistakes. You predict this customer will churn. You give a lot of coupons. That didn't work. Customers still churn. You wonder what's going on, right? So that's because the model is not working very well. It's not generalizing the findings. The finding is overfitted. So you want to preserve a portion of your training set as if they are new cases, and then that creates a testing environment for you to faithfully test the performance of the model. That's the idea. So to do that well, you want to make sure the training set and the test set are following the same structure. They are randomly selected, but the random selection process should make sure that the distribution of the data and the variables are almost symmetric to each other, or very similar to each other. And you want to have a way to ascertain that. The way to do that is to conduct hypothesis testing on key variables so that you know that the two variables are qualitatively the same, right? And there are two hypothesis testing common tests that you should use in almost all the scenarios. One is the t-test, which compares the mean of the same variable across the two sets. T stands for independent sample testing. You probably learned it from the basic programming test course or the quantitative foundation course. Both courses talk about that. In those cases, the tests are mostly for statistical purposes to test the significance of a regression parameter, right? To test whether or not the model is significant or not. The factor, whether or not the factor is significantly related to the response variable. But here, we use the hypothesis testing to make sure that we spot any signs of illness in the way that the data set is split into train and test. Normally in statistical exercises, you want to find significant results. And here, you don't want to find significant results. Why? When you don't have significant test results, that means the null hypothesis is accepted. The null hypothesis assumes the train and test sets are similar to each other. That's what you want. So in desirable cases, you don't find any significant p-values. That's when you can draw a conclusion the split is in good shape. That's the unintuitive part, but for this course, you actually use that for a different purpose, which is a good practice. So the textbook doesn't talk about these. The textbook doesn't say to use hypothesis testing to compare the similarity between the two sets. Only the slides talk about that. But the textbook talk about how to conduct hypothesis testing. So the testing procedure is a good reading from the book, but the purpose is I'm repurposing the test for the purpose of train test split for data science. One last comment would be to this formula. You don't have to understand too much. We'll talk about in detail when we talk about regularization in regression model or in logistic regression models. So for homework 1, and I want to highlight the requirement here. The question asks you to test, let's say for question 12, asks you to test, conduct the t-test for equal mean of the variable evening calls between the train and test set. So you will follow the procedure to implement the Python codes to conduct the test and get the test result, extract the t-value and p-value, interpret the p-value, and draw a conclusion. But so you'll do all of these, but before doing these, it's also important to understand how to state your research question, which is you're going to compare the similarity between the two sets on this variable, and how to state the null hypothesis. The slides include that. Here, this is the research question, or it's the question, by stating that. For the question statement, the question basically says that, so you can just repeat that. But the null hypothesis is something you want to construct by reasoning, by taking the question, right? The null hypothesis assumes equality, equal mean or equal proportion. You want to specifically, explicitly state that in your answers. You can write these as comments in the code cell, or you can write these as markdown cells and run them so that they look pretty. Either way, so you don't want to skip this portion, otherwise you lose points, even if your answer is correct, right? I would say 99.999% of train test split by using a good random split, the test result will be insignificant. The split will be healthy. That's most likely the case. But in the slides, close to the end, I show you that if you split it, not based on random sampling, not based on random split, but based on a systematic split, where you rank all the rows based on a variable that's, conceivably is related to the variable that you conduct hypothesis testing. Let's say evening minutes. Evening minutes is quite likely related to the evening charge, which is the amount of money that's charged on those minutes that are used on evening calls, right? Those charges are closely related to evening minutes used on the telephone plan. If you rank the customers based on evening charge and do a split in the middle, you have one group that's charged minimally, the other group that's charged a lot. These two groups are significantly different on this attribute. If you conduct hypothesis testing on equal mean of the evening minutes, you can be sure they're significant, they're different. The test result is different. So though that's when you get a p-value so small, that's clearly different. You know, that's when you reject the null hypothesis, and that's something that you don't want to happen based on a healthy split. So this exercise illustrates, this is not part of the homework, but this is exercise of demonstration to show the point. Hopefully you can catch up us. That's fine. Hopefully you can catch up. But I finished all I have to say. Any questions? Great.